8.1 basic ideas. In this section, and especially this chapter, we're going to be working with differential equations. And what is a differential equation? It's an equation involving derivatives of a function or functions. So it's gonna have dy dx's or y primes. And what we want to know is that basically what is a solution to a differential equation is going to be a function. So we also have something called order. We could do what prime or what degree is the derivative is the same thing then as the order of the differential equation. So y prime is a first order, y double prime is a second order, and so on. So we can also then have three examples here of different differential equations. And if you notice, letter A has the notation in dy dx form for a second or a double prime or a second derivative. So this one is considered a second order, and it turns out it's linear. It's a linear differential equation. And then it turns out B is also linear because what is the definition of a linear differential equation? Definition of a linear differential equation can be a first or second order, but it cannot have y squared, y times y prime, or sine y. So B is a linear differential equation because it doesn't have sine, and we are a first order. So it is a linear differential equation. C, we see y prime of t is equal to 0.1y times 100 minus y squared. This is a first order differential equation because we only have a y prime in it. But it is not linear because if we were to distribute this y, we would end up with a y squared in our differential equation. So this is first order, not linear differential equation. So then if we want to go ahead, another key concept I want to add in before we move on is this concept of initial condition value, or we call it initial condition. So we know we specify the value of y at a particular point. The key thing is when we're talking about initial condition, that if we have an nth order, it requires an n number of initial conditions. So if we have a third order, we need 3 initial conditions. So that's a concept that we need to remember before we move on. So for example, if I'm given this differential equation, notice we usually tend to call it f of t and y. So we're going to talk about things in a coordinate plane, but when it comes to differential equations, we're going to be talking not in the xy coordinate plane, we call it the ty coordinate plane. So this is a differential equation. This is your dq, and or dE if we want to put it that way. And then if you want, our initial condition could be for some A value. We'll call this the initial condition. Sometimes we would do C, sometimes in this case we're going to be doing some A's. We will also be using C's when we try to find coefficients. So these are initial conditions that we want to talk about. The thing is, when we want to talk about initial conditions, we're trying to take a general solution and pinpoint it into a particular solution. And one thing I'm going to note that on the page 553 in our book, it says final note. We want to know, once we find a solution that's an initial value problem, can we be sure there aren't other solutions? And given a particular initial value problem, how do we know whether a solution exists or whether it is unique? So these questions are proved by existence and uniqueness theorems, but those come in later courses. So we're always going to be talking about initial value problems that we can actually deal with, and we are assuming these are well behaved that we're talking about. So the most general way possible. So the initial value problems we consider in this chapter satisfy the conditions of this theorem, and we can assume it has unique solutions. So we want to go ahead and move on then. And I have this family of curves here. And you see the function is y of t equals c e to the 2.5t. And this is a general function. And then you notice that we have two specific or particular functions that are part of this family of curves. So because we're taking the antiderivatives to solve many of these differential equations, may end up with this general possible family. So once again, that initial value pins down the function. So that C is where it's going to be more of a coefficient, this transcendental function, rather than polynomial function. Here's our C, so that we can then pin down given some initial values. All right, so let's go ahead and try some problems. For number 7, we are given this function and we're given a differential equation, and we want to verify that this is a solution, that we're going to assume C is an arbitrary constant. So let's go ahead and given our function, in order to be able to substitute these values into the differential equation, I need y, they gave that to me, and then I'm going to need the first derivative. So I'm going to take the derivative of this function. So we know taking the derivative, c is just a coefficient. We know the derivative of e is itself, but we can't forget the chain rule. So we're going to have to multiply it by the -5. So there's my derivative of this one. And I'm going to go ahead and plug these two equations into my differential equation. So when I do that, I'll have the y prime, and then 5 times my original function, so 5c e to the -5t. Does this equal 0? Remember, we're trying to verify this. Normally, though, in this case, we're not doing like a check. We're trying to do a proof, so we're going to go ahead and not write that question mark. And then if we can see that we have -5 and a +5, the exact same, these are going to reduce itself to 0, and I do get 0 equals 0. So we've proved it. All right, moving on to number 13. For number 13, we want to verify solutions of an initial value problem. So we're going to verify the given function y is a solution of this initial value problem that we have here. So what we're going to do first is we're going to go ahead and we're going to do, I'm going to write steps, but you don't have to do that. This is just for my own self. I'm going to check that when I'm going to check with the y of 0 equals -3. So what I'm going to do is I'm going to plug it into my y function and make sure it's true that goes through this point. So I have -3 equals -3 cosine of 3 times 0. And then we go to check, and cosine of 0 is 1, and then -3 equals -3, and it is true. So then our step 2 of this then would be to find y prime, so we can substitute it into the differential equation, because then I have to verify that initial value, and then I'm going to see that I have to get y double prime. So I'll have to find it again, and then I'm going to go ahead and substitute. So I'm going to find y prime first. So I'm going to find y prime, and taking the derivative of this function, remember it's going to be the derivative of cosine is negative sine. So negative times a negative is positive sine 3t. But remember, we have negative 3 that was multiplying that negative, and then we have to do chain rule of 3. So 3 times 3 is 9. So I have a positive 9 sine 3t. So I have that, and now we're going to check the initial condition for number 3 using the y prime of 0 equals 0. So let's check that by saying, does 0 equal 9 sine 3 times 0? So sine of 0 is 0, and 9 times 0 is 0. So it checks. So then I want to go ahead and do another step where I'm going to take the second derivative. I need the double prime, so I want to find y double prime. And I'm taking y prime and I'm finding the derivative of that. It should be 9 times, remember the chain rule, so 9 times 3, or 27. And then the derivative of sine is cosine of 3t. So that's our double prime. And then next step is to substitute it in our differential equation. So step 5, where we have the double prime of t, which is 27, cosine of 3t, plus 9 times the original function. So 9 times negative 3 cosine of 3t. Does this equal 0? So we want to go ahead and simplify this, and we see that it's going to be a negative 27 cosine 3t, and that these do cancel each other out, or they reduce each other to 0, and 0 equals 0. So these do verify. All right, number 20 says find the general solution to this differential equation. So what we need to do is find y equals. We need to find the function. And that means if I'm given the second derivative, this is a second order differential equation, I need to go and take the antiderivative of this equation twice so that we can get down to y equals. So when I go ahead, I'm going to do the first set of antiderivatives. So remember, technically it's saying the antiderivative is setting it up like this. So if I want to remember, we're always going backwards, or the anti, so this would be y prime of t. And then taking the antiderivative of the right-hand side of the equation, I should end up with 5e to the 3t minus cosine 4t divided by 4 plus c. So we're taking that indefinite antiderivative of these functions. Now notice this though, because I'm going to have to take the antiderivative again, I'm going to call this c sub 1, because we could have more than one arbitrary constant now. So now that I have that, I'm going to go ahead and take the antiderivative again. So taking the antiderivative again, I see that this will be y equals 5/3 e to the 3t minus sine of 4t, anti-chain rule again, divided by 16. Remember, if we're given a constant and taking the antiderivative of it, we're adding in our variable. It was like t to the 0. Now add an exponent, divide by the new exponent. Remember, it's now an indefinite integral, so I now have another constant that I need to add in. So I'm going to do plus c sub 2. And then since I got it down to a y equals situation, this is our answer, or our general solution for this differential equation. All right, so next we have number 25. Given this differential equation and an initial value problem, we want to find its solution. So what we're going to do is take the antiderivative so that we can get y equals, and then we have an initial value to work with. So going ahead, oops, sorry, this should be dx. Started to write dy. In this case, I get y equals, oh, did that wrong. Sorry, let's go backwards. All right, so the difference one is this one. If this is a differential equation, we're going to see separable in another chapter section that if we would move this dx over, and then this would be, basically I wouldn't have to do anything here. I'd have the dy, and we're assuming it's a constant of 1. My dx would be over on the other side on this case. So we're calling this a separable differential equation. We'll separate it. And then if this is gone, and then from here, I can see that this would just be y, and then I'm taking the antiderivative of the right-hand side, and I should get x cubed plus x to the negative 3 plus a c. But now this is an initial value problem, so I want to plug in where y of 1 equals 0. So we're going to plug in this and solve for c. And that's the case. I have this, and c equals negative 2. So what I need to do then is plug that in for my c here for my final answer. So we should have, let me come back to this. Our final answer for this one should be y equals x cubed plus x to the negative 3rd power minus 2. And there we are.